Welcome to another CO2 Monday and the Refrigeration Mentor podcast. I'm your host, Trevor Matthews, and today I have a special guest, a friend of mine that I met actually at a CO2 event in Washington, the ATMO conference, which is a great event. I highly recommend if you're wherever you're at in the world, they put conferences on all over the world. Attend one of those. And this is one of those things where you network and you build relationships. So we got a great conversation on a topic that I don't know a lot about, CO2 extraction, and it's with the president and CTO of Vitalis Extraction Technology Company, James Seabrook. James, welcome to CO2 Monday.
Thanks for hosting me, Trevor.
Well,
Looking
thank you
forward to our
so much.
discussion.
Thank you so much for taking the time because this is a topic that I don't know a lot about, and I know I've talked with people about it before. I'm always intrigued to learn. I've been hearing about it for years and years, and I know we even talked before I even started Refrigeration Mentor about CO2 extraction when I was at Emerson, and now your company has grown immensely since our first conversation, and just even in the last year, it has grown a lot. And today, I really want to find out, and I know the audience wants to find out more about CO2 extraction and what's the difference between CO2 extraction and CO2 refrigeration.
And there's a lot of similarities. CO2 is a very cool fluid, and the same benefits that it has as a natural refrigerant, we use as a natural solvent. The business, I guess a little bit about myself. I'm James Seabrook. I'm joining you today from Kelowna, British Columbia at the Vitalis headquarters. Vitalis is a vertically integrated manufacturing CO2 technology company. So we've got a group of individuals in our R&D team that use our equipment to develop methods or applications of CO2 extraction. They will feed us information into the engineering team where we'll design a piece of equipment that meets those requirements, and then ultimately roll it out into the field where we can do all sorts of things across multiple industries. And we use it as a solvent, which is, in refrigeration, one of the reasons it carries oil really well, and it's important to have a good oil management system in your R744 package.
Yeah. Yeah. So you started around 2015, 2016. Now we're in 2023, which is amazing. How many systems in the last few years are all together that you have in the field?
CO2 extraction machines, we have upwards of about 164, I think, is the
Wow.
SKU that's on the floor right now.
Wow, that's huge. That's a huge amount. That's cool.
Yeah,
Okay, well, why don't
yeah,
we just dive into it and kind of find out a little bit about CO2 extraction because I'm really curious.
absolutely. I will share my screen here. I put a little deck together.
Oh, awesome. Yeah.
All right. Can you see the logo there?
Yeah.
All right. So as I mentioned, we're based in Kelowna, British Columbia. We've got about 40,000 square feet of manufacturing facility here. And we're an ASME and PED, which is a European Pressure Equipment Directive certified facility. We're also a TSBC contractor, an AU and MA license holder. So we not only design the systems, but we also build them, and we build everything from our vessels and our pump through a complete package and then install it. On the top left, you'll see one of our kind of standard 200-liter systems at a site out in Christina Lake, British Columbia, where they process tens, almost 100,000 kilograms of cannabis annually into oils. Those can be used in pharmaceutical applications or recreational applications. It's a new market, and it was Vitalis's main market when we started the business to provide a clean extraction solution. The picture across the top with the kind of different fractions of samples is an example of what a crude cannabis extract looks like. And what we're doing there is we're pumping supercritical or liquid CO2 over a biomass, dissolving certain molecules into it, and then separating those molecules out. This works kind of across a very wide range of applications. Modern dry cleaning, typically uses CO2 for garments, cleaning your clothing. The picture in the top right is an example of an aerogel that we manufactured by extracting the substrate with supercritical CO2. That's a structure similar to what's on the nose of the space shuttle, where it has really, really high insulating capacity, and it's very lightweight.
Wow.
And a new and really exciting area that we're working in is plant-based proteins and purification of natural products, where we can eliminate the use of toxic substances like hexane. In Canada, a lot of plant oil and food products are processed with various solvents, which we can replace with CO2. And it's kind of akin to the phase down of HFCs and hopefully the prevention of HFOs moving forward, where we have great sustainable solutions like ammonia and hydrocarbons and CO2 as natural refrigerants. Sometimes the end product is the oil itself, and then sometimes the end product is kind of what's left over in the machine. So the cleaned up protein powder, or the defatted fiber product, or the aerogel, whereas you could also have the output of that biomass or product like the oil be your main, or you get both, which is kind of the case in plant protein. One of the ones I'm really passionate about, everyone loves beers, and I like, big juicy IPAs.
Yeah.
CO2 extraction has been around for a long time. This is not novel. We operate in a range much lower temperature than historically CO2 processes have happened. So we've developed methods to create really clean fractions, and one of them is extracting from hop plants. So on the left, you'll see a typical hop cone vine. That's what would go into your beer. And in the middle of that, there's the lupulin glands, and those little glands, the kind of gold looking powder, contains all the goodies. That's your beta acids, your alpha acids, which relate to the IBU of your beer, and then also the flavors. So the pineapples and the peaches and the nectarines and the lemon flavor, all those terpenes that give the really nice aromas, come out in an oil, like the jar on the right. And that's straight out of our machine. So that's got no other processing in it. It was a dried hop cone with oils in it, and now it's an oil that's free of any type of solvent that can be put into your beer.
That is pretty cool. So in these systems, I'm assuming that you would have to have someone put the product inside it, and then it's a closed vessel where you are putting, I'm probably getting ahead of myself, but closed vessel where you put in all the product, all the hops, because I love hops and they smell beautiful as well, like you said. And then you have the process where it will run to pull the different oils out or the different product out, correct?
Yeah, absolutely. And here's kind of a basic example of one of our smaller machines, and where you would put the biomass would be in this chamber. One of the big differences between extraction and refrigeration is we operate in very different pressure ranges. Most of our machines have standard operating pressures up to 5,000 PSI. A high pressure refrigeration system usually taps out at 120 bar, somewhere around 1,600 PSI.
Yeah.
And there's unique challenges that go along with that, but there's also really good efficiencies, and various reasons we do it mostly is that CO2 can be tuned in solubility. So depending on the pressure and temperature that you're operating at, you can be very selective with what type of molecules you want to dissolve and carry through your system. So we start with liquid CO2 in our accumulators. That CO2 is usually sitting at saturation around 300 PSI. We pressurize that with a positive displacement pump. We can then control the temperature through a high pressure heat exchanger. That flows into, and I'm moving my cursor. Can everyone see that on the screen? Perfect. Flows over the biomass that would be in this chamber. We then depressurize it into a vapor. The oils would come out of this separator, much like your oil separator on the discharge of your compressor. And then we do some CO2 cleanup on the backside. And as I was just kind of mentioning there, in refrigeration, we see a lot of enthalpy charts. We work with this chart quite a bit to show operators the difference in parameters that you can achieve with supercritical CO2 or dense phase liquid CO2. And our machine can pretty much operate anywhere on this chart. So if you want CO2 at 4,500 PSI and 10 degrees Fahrenheit, then you can make the fluid condition adequate to go over your biomass at that. Or if you want to run at 4,500 PSI and 150 F, we can do that as well, which creates a really interesting demand for refrigeration, because sometimes you have more heat, more cooling, less cooling. And I put a little.
So when you're above that, when we talk about it in refrigeration, we talk about the critical point. When you're above 87.8, 1055 psi, which is a lot lower than this, it's a supercritical fluid. There is like no liquid and no vapor phase. It's a fluid phase. But when I'm looking at this diagram here, you're saying you could be running at 3000 psi as a CO2 liquid?
Absolutely, yeah. So if you're below that 88 degrees, you're still in a liquid phase. In a pH diagram, it'll look like it's in a supercritical phase.
Yeah.
And I think that's technically, you're above one of the requirements. But to be a supercritical fluid, you got to meet both. You have to be both above 88 and both above 1050. Awesome. And that's where you get the really interesting viscosity properties. And when you think of a supercritical fluid, and you look at, say, right up at the top of that line, say around 90 degrees and 4,500 psi, you have almost the same density as a liquid, but that fluid will fill the volume like a gas. So there's no kind of transitionary phase layer like you would see in a glass of liquid water, right? Where you have water in the bottom of your cup and then water vapor above it. So the glass is always technically full.
Awesome. Wow. That's so interesting to me, because this is something I've not even thought of before or looked at. So that's pretty cool.
Yeah, and in our machine, so we talked about kind of the different components, very similar to a refrigeration system. Instead of a compressor, we have a pump. Instead of a high pressure valve, we have an expansion valve on our separator. And then our process condenser is the refrigeration evaporator, which, when we started designing these systems and working with refrigeration techs and saying we're using CO2, differentiating between our process condenser being the refrigeration evaporator was always an interesting conversation.
So you're saying that when you talk to them, that you were talking about the process evaporator, is that correct? Or
condenser.
Condenser as the evaporator. Okay.
Yeah.
So this is what's real cool about CO2. There's all these different terminologies, and it doesn't matter what section you're in. Refrigeration is still refrigeration, and you just want to understand a term on the people that you're talking to. Because I see this like TD. You can talk to HVAC people, and then refrigeration people, and then supermarket people, and TD means different to them than how they take it. So that's a really good point on that. So I like that.
Absolutely. So this is kind of like the journey of a CO2 molecule through our extraction machine. We start, so we store our liquid at saturation. On the refrigeration system, that would be much like your receiver tank, right? Where you're taking liquid off the bottom to go to your evaporator. We're taking liquid off the bottom of our tank to go into our pump. So we start down here. We're usually sitting, like I said, between 300 and 400 psi, and that's really just driven off of our condenser temperature. or the refrigeration evaporator temperature. So in this whole process, our CO2 is closed loop. We recycle all of the CO2 that is being pumped over the biomass. And this example, we're going up to 4,600 PSI. So the first step is through the pump. We're going to do a supercritical extraction. So we're now going to add heat to that fluid after we've pressurized the liquid, and that's going to convert it into the supercritical fluid. And we're going to go across that supercritical point. And somewhere in this range would be our extraction parameters. And as we come out of that vessel, we depressurize through an expansion valve, and we want to limit the fluid's carrying capacity. So we want to be able to easily separate our heavy molecules or the molecule that we're targeting away from the vapor. And we do that by reducing the density and going from a liquid or a supercritical fluid back to a vapor. And then we have a minimum superheat recommendation. So to get good separation, we want a certain velocity in our cyclone, and we want a certain superheat to make sure we're not filling up our collection vessel with liquid CO2. So you can see in this chart here, we've got almost 50 degrees superheat in our separator, where we're going to allow that oil to drop down, that CO2 vapor to go back up, to be then condensed back into a liquid and recirculated through the process.
Okay. So the where it starts, you know, you're at saturation, then you have your pump. So to get it up to 4,500 pounds, I'm assuming you have that pump on a VFD and you ramp it right up. How do you get it from 1,000 psi or 300 psi, sorry, all the way up to 4,500?
We do it in a single step, and it's a pump built by Vitalis that is a hydraulically actuated positive displacement pump.
Okay.
The reason we chose to do that is we do all of our pressure and flow control on the hydraulic side.
Okay.
But we take liquid in, check valve on the inlet, check valve on the outlet, and then we push it in one stroke up to 4,500 psi.
Wow. Okay.
Liquid CO2, even though it is compressible, it's not that compressible, which is one of the reasons we chose to design our equipment with liquid CO2 pumps. Is we get much better energy efficiency in pumping a liquid than we do compressing a gas or a vapor.
Okay, so you get this pump, this liquid CO2 pump, you get it up to 4,500 psi in this example, and then you have this heat exchanger, and really the heat exchanger is to put you up to that supercritical, because right now we're at 10, 20 degrees Fahrenheit. So you heat that liquid CO2 up, and you push it all the way up to about 140 in this example degrees Fahrenheit. So you're getting it into the supercritical phase, and you do that to get a specific to a specific point to pull out that oil, or why do you pick 140 over 120? We'll say what is that reason again?
The solubility of the oil in CO2. So different oils have different solubilities.
Okay.
Much like why you select a certain oil dependent on your refrigerant type. And we want to target something, then we can choose where we want the CO2 conditions to be when it touches that oil. Okay. So for a hop extract, where they're very light, volatile chemicals or compounds, we run very cold and very low pressures versus like omega fatty acids that are in plant proteins that we want to remove, where we need higher temperature and higher pressures to get those into solution and carry them out of the biomass matrix.
Super cool. So that makes sense. So different temperature, different supercritical areas will get the different oils out, and then from there, as I look at it, you have an expansion valve, and that expansion valve is going to pull you down through your cyclone, or is that after your cyclone separator?
Just before our cyclone separator.
Just before. Yeah. And so that there, as you pull it down, you drop the pressure, you drop the temperature. So we go from 140 Fahrenheit all the way down to 60 Fahrenheit. And that temperature there is also, do you always stay at 60 or do you move that around as well to now extract the rest of that oil, or how does that exactly work?
It's going to depend on where your CO2 is being stored at, because if it cascades down from the cyclone to the storage vessels without any other pressure drops. So that's where I was talking about the superheat.
Mm-hmm.
If you had your CO2 in the accumulators at 800 psi, and your saturation temperature then is closer to say 65, well, we're still going to recommend you have a superheat there so that you get good separation
Yeah.
between liquid CO2 in your collector and vapor coming out of it. And that expansion valve, if we were to correlate it to the refrigeration, that's where all your Joule-Thomson effect of cooling is happening. So we got to pump a lot of heat into that fluid as it's going into the separator so that we don't build up liquid and essentially end up with a flooded evaporator in the refrigeration terms.
Yeah. Okay. And that makes sense. So inside these vessels, I'm assuming the heat exchanger and the phase management is similar to a shell and tube heat exchanger. Is that correct?
Correct. Yeah.
And then the extraction vessel, what would that look like inside? Because I'm assuming that's where you put all your plant product or whatever product you're extracting from. What would that look like inside?
Just an open tube with a kind of diffusion plate on the top or on the bottom, and the filter screen on the top.
Okay.
And
Yes.
then in some instances, we'll maybe have a cartridge you can put in there with product already in it, or a bag that you can load in, or you just pour your stuff in and vacuum it out afterwards.
Yeah. Okay. So that extraction vessel would be something that would have to be cleaned after each process, or after you do your extraction. And then down the separator, what does that look like inside? Just to give people a kind of a visual.
Those are jacketed, so we apply heat on the outside, usually with glycol, and on the inside, again, just a basic tube with a free draining bottom. And depending on the application, there's sometimes demisting pads or a filter element or some other thing at the top of the vessel. But most of them are just an open separator, and we rely on the speed to push the heavier molecules or oils out and allow the gas to go up through the middle and the top.
Okay, that's really neat. That's really neat. So I'm assuming right at this point that different biomass, so different plants or different will take different amount of time to extract. Is that correct?
Absolutely. Yeah. And how much is in it, right? If you put, say with plant protein extraction, if I put in a whole seed, like a whole canola oil, and it's got 50% by weight oil in it, there's a lot of oil to take out. Or if that had already been screw pressed and now the raffinate product only has 10% oil in it, then that can be done much quicker, because there's always a solvent to feed ratio of how much CO2 you need to flow per kilogram of available oil.
Well, and so when you say screw press, is that already doing some processing of the plant? Because I never heard that term before.
Yeah, it's a mechanical separation process that most oil seeds go through for
Okay,
collection.
awesome.
Yeah, not something we do though, but
Yeah, yeah. But
this is something that you could put on the back end of that process to recover what would historically be a waste oil and also clean up a high value plant protein product.
that's super neat. Okay, and so for those who are listening, like he has this plotted on enthalpy diagram showing the different locations, and we've done this before at many
Pressure and
trainings.
temperature diagram,
Oh, sorry,
not
pressure and
enthalpy.
temperature
Yeah.
diagram, not enthalpy. Yeah, pressure temperature diagram. Thanks for correcting me. But we've done this many times before, and I do this in my trainings all the time. And it's very important to look at these and plot the different components in your refrigeration systems. And it's really good in CO2. I do it all the time, just to show, give a visual of it. Like
Yeah, and so again, this is not the typical enthalpy diagram that we'd expect to see a refrigeration process on. But I thought it'd be kind of cool to show that the range of CO2 refrigeration is pretty tight, but very similar in this chart of capacity depending on your process. So the colder that we want to keep that liquid, the farther down to the right we need to go on temperature and pressure. And the more heat we want to reclaim, the higher pressure and farther to the right we have to go on the discharge side of those compressors. So all the same components in a refrigeration system here. Again, the trip of the molecule, if we start at what is the CO2 evaporator, the refrigerant, or the R744 evaporator, that's where we're recycling the processed CO2. So we're boiling on one side, condensing on the other side. That now vapor is going through our LT compressor. Depending on the system, we might have a flash gas bypass valve into the empty, and then we go up to our heat reclaim area. And when you overlay those, you can kind of see how our refrigeration system is actually working like a heat pump or a chiller with heat recovery, whichever way you want to say it, to utilize that waste energy to boil our processed CO2 and then recondense our CO2 all in one.
Yeah, no, that's super neat. I really like. I can't wait to see one of these processes, which is really cool. So in the system, then, so these are closed loop systems, but you would open it up, you'd put in your product, you'd close it, you'd run it, and then I guess you would isolate it after. I guess there's certain isolation valves where you would shut it off so you don't lose any CO2. It stays in the system. And is that CO2? Do you have like any filters? Does any of that biomass, that oil, get into the CO2 liquid, or does it stay separated because of that cyclone or separator?
The cyclone separator removes probably 99% of what we're stripping out, but we spend a lot of time developing ways to clean up CO2 and recycle it continuously, because you just identified a big culprit. If you get a contaminated solvent, it can change the properties and lead to undesired extraction. If you have a lot of water in your CO2, you could co-extract chlorophyll, which can make your product a dark green color. We can also form carbonic acid with CO2 and water forming in it, and biomass always has water in it. So water management in your system is very important. And the three vessels basically after our separator are all for CO2 cleanup. And that's a very important part of the process. One, for ensuring good solvent quality, and then also making sure that you're not venting a lot of CO2. These are small machines, typically operate in like the 10 to 20 kilograms per minute of CO2 flow out of the pump. But there's large systems out in the industry that have 500,000-600,000 kilogram per minute CO2 flow. So that's a lot of CO2 if you're not recycling it.
That sounds like man.
Yeah, we do lose a little bit when you open up the chamber, but we bring it back down to saturation. Then we have a recovery compressor that can bring it down lower as well. Cool. So on each run, we're probably losing less than 2 or 3 kilograms.
Okay, yeah, that's pretty neat to understand that going through the filtering process, first extracting the stuff, going through the filtering process, and then losing very little of the CO2 in the process. That's super neat. I really like the layover too. Like, so you do have to have refrigeration for CO2 extraction as well. And I know I'm assuming before there was a lot of CO2 refrigeration system as it's continuing to grow over the last 5-6 years. Have you transitioned from doing like synthetic refrigerants on that refrigeration cycle that you needed to CO2 yet?
We have one system operating in the field with CO2. It's in Denmark. So that unit's using an advancer condensing system.
Cool.
And most of our systems are operating on 404, 507, 448, the newer systems. And then starting this year, all of our Vitalis systems will have an integrated R744 system.
Wow, that's
Yeah,
awesome. That's awesome.
it's
And
really
so,
exciting.
are you building the now? So, are you going to be building those refrigeration units yourself? Vitalis will be building them, or are you outsourcing that?
We are, yeah.
Awesome.
We'll be packaging them right onto the skid, so that all of the heat reclaim that we're looking at here. So when we talk about the red lines that are going up from our gas cooler / heat recovery, that's where we're putting energy back into the system, and that can either be done. We have a high pressure heat exchanger where we actually discharge the empty compressor directly into a heat reclaim with CO2 on the other side, and then also into a glycol loop. And then the glycol is pumped around through the system. And then the extraction process gives that energy back through the evaporator down at the bottom there, where the cyclone is spitting out that heated vapor, and then we're condensing all of that CO2 back down.
Awesome. So yeah, because that makes sense because you need to get that heat for that phase management because you're pushing that 40, I think you said 4,500 psi liquid. You need to get it to a certain temperature to extract properly. So you need that heat. And now you're using that discharge of that refrigeration unit in that. That's super neat. Super cool, man. I love it.
Yeah.
So
And that's what allows us to recycle the CO2 continuously, is
yeah.
having that refrigeration capacity. There are some smaller systems that operate as an open loop, and we weren't really keen on doing that. I think it's responsible to make sure you keep as much CO2 out of the atmosphere.
Yeah, and I think that is so awesome that you're doing that because I even talked to so many technicians and contractors like, oh, it's CO2. If I need to do a repair, I can just let it rip. No, CO2 is still not good for the environment. It's better than other refrigerants, but there's still a GWP of 1. It's still, we don't want to release this stuff to the environment. Do our best because at some point CO2 is going to be regulated as well. You're not going to be able to just let it rip into the atmosphere because back in the 50s you could let R12 go. You know what I mean?
Yep.
So now it's gonna come to a point. I know for sure. I'm telling you right now. There's going to be regulations on CO2. So start learning how to reduce releasing to the atmosphere. Awesome. So
Absolutely.
you've been doing this for since 2015 or 2016 you started. What are some of the trials and errors over the last 7 years that you had to figure out that was kind of like, wow, this is really a good learning curve, some of the things that over the years that you developed to get your process to where it was or is.
Yeah, a lot of that falls on the R&D team. So every time we have a new type of biomass, there's a new set of parameters that we need to develop to optimize that process. And we focus a lot on optimization from like an energy and operational cost perspective. So yes, we could pump a lot of CO2 over it and do the process really quickly, but did we really saturate the solvent? Is that producing the best quality of product? There's so many variables when working with natural products that are even sometimes subjective. So in hops, right, you could create the perfect extract, but if it doesn't go into the beer or produce the experience that you expect from that beer, you actually have to tune it differently to make that end product. So we like partnering a lot with our customers to help solve those problems. And they've always got really smart people that will help us, develop the SOP as well. From an equipment standpoint, the refrigeration side has always been a challenge because we ship our extraction machine and we ship a condensing unit, and then the customer has to work with their trades to connect them. Not everyone's always familiar with low temp applications. So there's a lot of education that has to go on in working with those trades to get the equipment operating properly. And that's one of the reasons why we're going to package it kind of on the skid now, is to really simplify that commissioning process where Vitalis can support both commissioning the extraction machine and the extraction process, but also fine tune the refrigeration for your environment and your process itself.
I think that's super smart doing that. making it easier for the customer as well as their contractors. Because once again, CO2 is like 1% of the global market, and it's just another layer. Like, and you said, some people don't understand low temp application, let alone low temp CO2 application need be. So I think it's smart to do that. And I know that this will be very successful when you have your own full package unit. Less hands in the pie, I guess, be able
Hmm.
to make mistakes.
Yeah, and we've gone through all sorts of optimizations. So we're continuously adding automation, right? Learning which parts are best controlled by the PLC instead of an operator. That's been a lot of fun, and there's always technical challenges there. Generally, when you talk with vendors, valve vendors like Swagelok or Hylock, about high pressure or supercritical CO2, it's sometimes an unknown state, right? So then you got to work through material compatibility issues. You got to work through pressure compliance. You got to work through valve design issues, particularly when you have maybe small particles of biomass in your valve, where you have a high concentration of oil at the beginning and then a lower concentration at the end. We recently introduced the ability to use a co-solvent. So we can inject a small amount of alcohol into the CO2 in order to tune the polarity and extract other things that CO2 wouldn't extract. And then we separate, that co-solvent in our separators, and we move it out of the process. Every time you add a new variable, the components react a little bit differently, and then the engineering team has to, make it come back into where we want it.
Yeah, no, that sounds like it sounds like a fun journey. I know you've been doing this for a while, but it sounds like the learning is just exciting each time you get into this, working with the R&D, the new components. And this is what's great about working and talking with people about CO2 is, and I can tell when I talk to you about it, you just have a smile on your face talking about how the process works and how the system and the R&D teams work, and just all this learning, you know what I mean? And I think it's pretty awesome, pretty cool. And I've learned a lot so far just to understand that pressure and temperature side of it. That's huge for me, because I see
Yeah, and
this growing. Like this market is going to be so huge. It's going to continue to grow. It's big now, but it's going to continue to grow, especially on the health side, like you're talking about extraction on different plants and things like
absolutely.
that.
Yeah, and we've kind of incorporated CO2 into all of our products. So these are kind of our four main product lines. Our Polarimax, our extraction machine, that's a primary mobile phase of CO2 as a solvent. And again, we can use co-solvents. Cool Shift is going to be our product lines of refrigeration and heat pumps that are integrated on our machines, and then also kind of operating as standalone R744. And then we're also in the process of doing small carbon capture systems to recover CO2 from waste sources where it maybe wasn't previously economically feasible. So we're very passionate about CO2
Yeah, no,
and
this
focus
is
on it
super neat.
within kind of all the markets.
Yeah, so right now, have you've designed each one of these sections and you have these in the field, or are there any of these that are up and coming, like the carbon capture one? I think that one there is very interesting. I'd love to learn more about that one. Do you have those in the field running right now, or is that something in the works?
Those are all prototypes, probably be Q2 of this year.
Awesome.
Yeah,
That is
but
super
Polarimax and Aero, we've got those in the field. Yeah.
awesome. Yeah, that is super neat. And this is what's so cool about CO2. There's so many different verticals and new verticals all the time coming out. And I'm excited to see. I'm excited to see more of this.
Yeah. On the Cool Shift front and refrigeration, I know that's where your expertise and I think a lot of interest lies for people on the call as well. Is these are kind of the scale of systems. And what I'm really passionate about too is our vertical integration. So when it comes to custom manufacturing equipment, this is a project with I think your good friend Winan at FGN. So this is a large liquid overfeed system that's in the shop right now.
Wow.
And they've been excellent to work with and help us learn as well. But oil management, receivers, large pressure vessels, it's all what we enjoy doing, and it's been a lot of fun to work with our engineering team and our fab team and our assembly and our technicians to get everyone on board with the future, which is natural refrigerant.
Yeah, no, this looks super cool. Like this is a massive process. So anybody who's listening, like you got a massive, looks like a flash tank there. The
Yeah,
massive rack of Durin compressors, which is really good. I had Giacomo on last week talking about their compressors, which they're amazing. So
yeah. So this will have that's a 5,000 liter circulation drum. So on this skid, we're going to use centrifugal pumps to move liquid CO2 out to the cooling load. We get a mix of liquid CO2 and vapor back, and then those Doran compressors are taking all that vapor and pushing that heat outside. Pretty big receiver up on the top right, and then large oil management system, because when you've got that much liquid CO2 in your system, you need to make sure those compressors are getting fed well.
yeah. Oh man, that looks awesome. I love seeing this stuff. I love seeing, innovation happening, and that's super cool, James. This is super cool. And is there anything else you'd like to add on extraction and things that you've learned? Because I've learned a lot today, just understanding the differences between and why you're doing this. Anything else you'd like to add?
It's so interesting because you might not even think there's an application, and then it's been around for so long, but really not well commercialized. There's a paper you find from the 80s where somebody at a university tried something, and it can lead you down a rabbit hole of reading literature until 2 a.m. in the morning. Like it's really endless. So what we can do with CO2 as a solvent, as a working fluid and power cycles, I think is really cool. So replacing a steam power cycle with supercritical CO2 has all sorts of advantages, and there's quite a few projects going on worldwide where they're doing it at huge scale. Refrigeration, I think, is super exciting as well, because of the high COPs that we'll be able to get, and completely decarbonize our extraction process from an energy perspective. So as long as you're using renewable energy sources, which in BC and obviously lots of Canada we are, the high COPs in our application, how it pairs so well with extraction is cool. But yeah, botanical extraction is one thing. CO2 as a cleaning solvent for high precision, metal applications or biomedical implants, material science, spray drying. There's so many things you can do with a supercritical fluid, and particularly supercritical CO2, that the opportunities are really endless.
I love that.
Which always keeps you on your toes.
Yeah, no, that's super cool. So James, how can people find out more about you, get in contact with you, and just really be able to find out more if they want to learn about your company and Vitalis?
I can be reached at James at vitaliset.com. There's also some contact forms on our website, which is vitaliset, as in extraction technology.com, and LinkedIn as well. If you want to throw me a connect, be happy to chat more about different applications of supercritical fluids,
James,
and extraction technology.
James, I want to thank you so much for taking the time to do this. I learned a ton. I know the audience learned a bunch. And reach out to James. and his team, if you want to learn more about this stuff, because I know there's a lot of people that are interested in learning more about CO2, and this is interesting to me. I'm sure we'll do another one of these. James, thank you so much again for stopping by CO2 Mondays with Trevor. Thanks so much.
Thanks very much for hosting. I'd be happy to do another one. Yeah. What's your next conference you're going to?
I'm going this week to HVACR Symposium, and then I'm going to AHR, the expo.
Right on. And where do you think people who want to learn about R744, what are the best conferences to go to in North America?
The best one's probably the one that I know of right now is that Atmosphere. Yeah, Atmosphere is probably the top one to go to. And then globally that I know is which Chilventa was in October, so that'll be
Oh yeah, I
2
missed that one
years.
this year.
That one there's where you're gonna see a ton more. In 2 years' time, I'll be there again. There's so much CO2 there, and I'm hoping. I know for sure at the ASHRAE show, the HR Expo, there's going to be a lot of CO2 this year.
Right on.
Awesome, James. Thank you so much. Thanks, everyone.
Thanks. Bye for now.
Hey, thank you for watching this video. I do hope it is bringing you a lot of value. If you are looking to grow and build your refrigeration teams and want them to learn CO2 refrigeration, head to the refrigerationmentor.com website, click to contact us, and let us know how we can build a culture around training inside your organization. Let's get a conversation going.